Hello and welcome to video number 4. Today we will estimate a linear state space model using the prediction error method. And I'm here in the Pluto notebook, and we're first gonna have a look at the particular state space model we're gonna estimate. So we have a model where the state x in the next time step is equal to ax plus bu plus some little correction term k times epsilon. And epsilon here is the prediction error. So it's the difference between the output of the model. The output of the model is y is cx plus du, and the data here yd. So at each time point we have some measurement of the output, and we compare that to the model output. Sorry, there should actually be cx plus du there, like that. All right. And that forms the prediction error. And the prediction error method simply minimizes the sum of squared prediction errors here. It doesn't have to be the sum of squares. It can be the sum of absolute values or something like that. But typically, sum of squares is quite common. And we optimize this criterion with respect to the matrices A, B, C, and D of the system model, but also with respect to the prediction gain, or sorry, the correction gain K, and the initial condition x0. All right, so these matrices A, B, C, and D, they have a lot of parameters. In fact, they have more parameters than the actual number of degrees of freedom in a system like this. And that's because we can apply any arbitrary invertible similarity transform to this system and still obtain the same input-output map. So in the prediction error method implemented in control system identification, we have chosen a particular parameterization where the A matrix is tridiagonal. And if you're interested in why we did that, there is a reference in the doc string that explains that that might be a reasonable choice. All right, and since this is a gradient-based method, we need a way to derive the gradients of this cost function with respect to these parameters. And traditional implementations of the prediction error method, they derive that gradient by hand and hand code that. And that's quite annoying and slightly difficult to get right. But since we're doing this in Julia, we just derive the gradient using automatic differentiation. And if we do that, implementing the prediction error method is actually very straightforward. We just take in all these parameters. We form this model, and then we just simulate this model to compute the predicted output. Then we compute that predicted output to the output in the data, and we form this sum of squared errors cost function, and then we optimize that. So in our case, we just pass that cost function to one of the already existing optimizers in the Julia ecosystem. Right, we also need to initialize. Since this is a gradient-based method, we need some initial guess for these parameters. And in our case, we actually estimate the model using subspace-based identification, which is a topic for a future video. So we use that to initialize it, and then we refine that model using the prediction error method. We could also imagine having a prediction horizon that is longer than 1. So this here, if we optimize this formulation, we optimize the one step ahead prediction error. We could imagine predicting more steps into the future, and indeed sometimes that's reasonable, and the prediction error method implemented in control system identification supports that, but we're not going to make use of it here. All right, so we start by loading some packages, control system identification and control systems, and plotting and some standard libraries and so on. Then we have some experimental data here, and the system we have some experimental data from is depicted here. It's a system with 2 masses, and they are connected by a spring and a damper. So C here is a damper, and we can exert the force on the first mass. So this is a very common model of position control systems where the first mass corresponds to the motor, and it has some inertia, maybe it's rotating. And then there is a gearbox or some other flexible transmission, and then we have the load mass, the thing we want to make moving. All right. And since there is some flexibility here in this transmission, we get kind of a resonant system. And the experimental data we have here is actually not experimental, it's simulated so that we can compare to the true system model. And we see that the input here in the bottom plot starts, it's a low frequency sinusoid roughly, and then that frequency increases for the duration of the experiment. And we see the output here in the top plot. We see that first we have a large output, and we have a smaller one, and then we seem to have some resonance here around this frequency, and then we have very low amplification for higher frequencies. All right. So, since this is supposed to be a mechanical system, when mechanical systems move, there is always some friction. So I have actually added a small amount of non-linear Coulomb friction to this data as well, which makes the overall system non-linear, but we will still make use of a linear model for our estimation, and we will see how that works. All right. So here we have the code that generated the data. We started at one particular frequency, 1 Hertz, and we ended at 7 Hertz. So the chirp span starts at 1 Hertz and ends at 7. So this also means that we can only really hope to estimate a good model in this frequency range between 1 and 7 Hertz. For much higher frequencies than that, we just don't know how the system behaves, right? But we see already here at 7 Hertz, the output of the system is very, very low. So we don't expect to be able to estimate anything above there anyway. All right. And then here is some code for adding the friction model. I'm not going to go into detail exactly how that works, but if you're interested, the notebook is of course available on JuliaHub. All right. And that gives us an input-output data set of length 2000 points. And it's sampled every 100 times per second here. So whenever I get data set like this, I like to first perform a non-parametric estimate of the transfer function. It's a size of system, so we can easily estimate transfer functions. And non-parametric just means that we make use of the FFT in this case. So we know that the transfer function of a system G is the ratio of the frequency representation of the output and the input. So we could compute this. We could compute the FFT of the output and the FFT of the input, and that would give us kind of an estimate of the transfer function. All right, underneath the hood, we don't do exactly this actually. We do something slightly smarter, but in essence, this is the thing we're computing here. And we can do that by calling TFEst for transfer function estimate. And if we plot that, we get something like this. So we see we have high amplification for low frequencies, the blue curve here. And then we have a notch and a resonance peak. So this particular frequency here for the resonance peak is where the masses vibrate the most. And I have marked here with these two vertical lines the start and the end of the chirp. So we see we think that between those two lines we should have a good model of the dynamics, but outside of those two lines we can't really rely on the data, the model too much, because we didn't actually send any excitation in there. And indeed we see above the frequency here the estimate starts getting extremely noisy. All right, so this is gives us a nice overview. We expect one kind of resonance peak in this model. All right, so now we will move on to perform the actual prediction error estimate. We will estimate two models, both of order 4, because I happen to know that two masses, they each have one position and they each have one velocity. So you require in total 4 state variables to represent that. So that's why I don't need to guess the model order, I already know it. All right, so I call the function u prediction error method, and we pass the data and the model order. And here I just say don't show the trace. The trace is the logging info during the optimization. And I say that I don't require this model to be stable. And the reason is that we have poles on the stability boundary. We have an integrator. And then I estimate one more model, and for the second model I say focus on simulation. So by default, prediction error method solves an optimization problem that tries to maximize the prediction performance. But if we say focus on simulation, it doesn't use the predictor, it doesn't use the K feedback gain to incorporate the data. So it solves the simulation error minimization problem. All right, and here I actually show the trace just to show that it's an iterative method. It took around 50 iterations this time. But you see, even though it's iterative, it's fairly quick, 0.06 seconds. It says here the entire cell executed in 100 milliseconds. So for small model orders and reasonably sized data sets, this method is still very quick. Right, so now we have two models, model P for prediction and model S for simulation. We see that this prediction error method also returns an estimate of the initial condition and the struct returned by the optimizer with some status of the optimizer. So we can evaluate it. Here we call the function simplot for simulation plot. That will plot the data and the simulated output of the model. And we compare here the model estimated using prediction error minimization in orange and simulation error minimization in green. And we see that here, where the output is large, they are both fairly good. And then here where the output is small, they are both quite bad. All right. So why are they quite bad here? And the reason here is that this system has a double integrator, right? Where the input is torque or force, and that's integrated twice to get position. And due to the small amount of Coulomb friction, so this non-linear friction that can't be represented by a linear model, if we integrate a small error twice, we will get a drift. If we integrate it once, we will get a drift, and if we integrate it twice, we will get kind of a even worse drift, right? So the fact that this drifts off slightly here for low frequency, that's fine. We have a low frequency error here, but we see that the high frequency variation here, maybe they are still quite accurate. So that's not a problem in this case. We don't expect to be able to do well in simulation, all right, for this kind of system. But we can compare how we perform on one step ahead prediction instead. So here we just used simulation. We didn't use any measurement feedback during the simulation. If we perform one step ahead prediction instead, we see that now this low frequency drift has disappeared. And here we only have one model because the simulation error minimized model doesn't have a predictor, so we can only test the prediction error model here. And we see that if we predict one step into the future, we have a very good fit. If we increase the prediction horizon here, we will see that the fit will go down, but not dramatically so. So if we predict 20 steps into the future, we see that, yeah, now we have some error here, and we don't really have the correct gain here, and so on. And that's fine. It's more difficult to predict further into the future. But the critical point to remember here is that we have removed this low frequency error because we used measurement feedback. So I can pull this slider a bit back and forth to make it easier to compare. All right, we see that around here, around the notch, it becomes more difficult to fit the data for longer prediction horizons. All right, so the prediction error performance appears to be quite good. All right, and now since this is an simulated data set, we have access to the true model. We can actually compare in the frequency domain to the true model. And here we see the true model in blue and the prediction error estimate in orange, simulation error estimate in green. And we see here between the two frequencies that are included in the chirp, the magnitude here in the border plot is quite accurate. All right, so that's good. But outside of these frequencies, so frequencies we did not send into the system in our data set, we see that the fit is not quite as good. And in particular, the phase curve is quite inaccurate outside of these frequencies. So we see for very low frequencies here, the true system has a phase of negative 90, whereas the models have a phase of negative, what can this be, 160 or something like that. We see exactly here on the resonance peak, we have a good phase match, but even very close to, even within the frequencies of the data here, we see that we have a phase mismatch. All right, and in this case, this is due to that non-linearity implied by the friction. All right, so this is a good indication that if we design a controller using this model we have estimated here, we need to have a reasonably good phase margin because our phase in the model is actually wrong. Right, and we can see that in the Nyquist plot also. So here I show the Nyquist plot of the true system in blue and the models here. So if we think that the phase is given by the orange curve here, so that's the estimated model, then we might actually design an aggressive controller, but then we look at the true system, it actually has much worse phase, it's closer to the critical point. So this just shows that we need to have a reasonably sized margin. We need to be far away from this critical point whenever we use a model to design our controller, because the model is wrong, and in this case it's wrong in exactly the uncomfortable direction that takes us towards the instability, right? So here, this Nyquist plot I've closed the loop with a static proportional controller with gain 30, just to make this plot interesting here. Right, so this highlights very well the importance of having a good phase margin when we do model-based design. Right, we can also have a look at the pole zero diagrams. So in blue we show the true model, and in orange we show the prediction model. And we see, I hope that's visible in the video, we see that the true model has an integrating pole in the origin, whereas the two estimated models, they have each a pole here slightly into the unstable region. So the simulation models estimated by those are actually unstable. All right, and that's something that can always happen when we perform model estimation. We said, sorry for the scrolling here, when I estimated these models, I said stable equal false. If I had said stable equal true, which is the default value, then the prediction error method implementation would move these poles into the stable region after the estimation. But it didn't do that here since I said stable false. We also see that we didn't accurately capture the location of the zero. All right, and that's known both theoretically and practically, that it's difficult to capture zeros. Indeed, a zero is placed in the frequency domain where the model doesn't have any output, so it's difficult to identify the location of that very accurately. But even the poles here are quite a bit off from the true poles. All right. So here we learned that the simulation models were unstable, but we can look at the learned predictor also for the prediction model. And we see the predictor is actually stable. And that's good, because if it wasn't, then even our prediction would diverge, and that would be bad. So here the predictor has two poles on the very, very close to the imaginary axis, but it's stable at least. And you might see here that I call D to C on all my models before I plot the pole zero diagrams. And that's because we have estimated models in the discrete domain, but I find it easier to visualize poles and zeros in the continuous time domain. So this is discrete to continuous. It applies the inverse transformation to what C to D does, continuous to discrete. All right. We can have a look at the parameterization in the model. I said that we parameterize the A matrix as a tridiagonal matrix. And indeed, we see that here, that we have the main diagonal and the first sub and super diagonals are non-zero. But beyond that, we have zeros in the A matrix. But the B and C matrices are fully parameterized. The D matrix here is zero, and that's because the by default prediction error method will force the D matrix to be zero. You can give an option and say that you allow a non-zero D matrix, but most of the time you would like the D matrix to be zero. All right, so these model coefficients now are given in a particular state space basis that were just chosen by the prediction error method without any constraints whatsoever. This doesn't correspond at all to the true system model basis that is comprised out of position and velocity of the two masses. So since we have access to the true model here, we could actually try to transform this estimated model to the same basis, state space basis, as the true model. So this is of course not possible to do if we don't have access to the true model, but here we do. So we can go through that exercise. So there is a function called find similarity transform, and it tries to find a similarity transform between the estimated predictor model and the true system model P. And it gives us a transformation matrix here. T is 4×4. And then we can apply that transformation matrix to the system model, the model we estimated. So here we apply the similarity transform, and then I have a little function to truncate zeros and round the coefficients, so we will have something nice to look at here. And this is the result. So this is the estimated model transformed to the basis of the true system model. And we can compare that to, sorry, it's hard to actually compare. I minimize the code. Here we have the true system model. And we see that we have done a fairly good job, right, of capturing the true coefficients. So we have 0, 1, 0, 0. That's the equation of the first position. Then we have the equation of the first velocity, -100 minus 200 and 1. Here we also do very well. And then it's a bit more difficult to estimate the model for the second mass. And that's because the output of this model, the measurement, is the position of the first mass. So we don't have any access to the position or velocity of the second mass. It's a bit more difficult to estimate the dynamics of that. But it looks like we have done a decent job at least. All right. And here we have just the code that creates the true system model. So this would be unknown in a practical situation. Discretizes that with the sample time. Here we have the Bode curve of the true model. And here we have a function called chirp that generates a excitation signal that starts with a low frequency f0 and ends with a high frequency for a duration of tf seconds. All right, so before we conclude this talk, we will look at the advanced options of this function that performed the model estimation new prediction error method. And here in Pluto, we can always have a look at the live doc panel. It's available here, and that gives us the doc string for this function. But we can actually also go to the online documentation. It's available from the control system identification repository. And then we go here in the left menu to statespace estimation. Let's see if we can make it a bit larger. And then we click at the prediction error method. It goes through in detail what kind of model is assumed underneath the hood. It shows some usage example if you would like to see more examples. And then it explains the different arguments. So we can focus on either a prediction or a simulation. We can provide a regularizer. We can force the model to be stable or not. We can force the D matrix to be 0 or not. We can optimize a several step ahead prediction error. So by default, we optimize the prediction error 1 step ahead. And then it talks a bit about the internals, how you can use the model that you obtain after the identification and so on. And if we look at the doc string for the prediction error method, we see that there is something called an argument called output nonlinearity and input nonlinearity. So this function can actually estimate what's called Hammerstein-Wiener models. So models that are linear systems, but there is a nonlinearity on either the output or the input. And that's quite common. So we can estimate that kind of models also using this function. All right, that concludes the talk on the prediction error method. So to summarize, we have estimated a state-space model, a linear state-space model on this form, where we have this additional corrector gain k. So that would correspond roughly to a steady state Kalman filter. All right, thank you.